So we will start the session again. Good afternoon, everyone, and welcome. So this week's discussion was basically oriented along the solutions for compressible flow. So last time I spoke a little bit about how compressible flows and incompressible flows solution methodologies differ from each other because of the fact that for an incompressible flow, the density is constant and invariant. So when it is invariant, we are unable to use our normal ideal gas equation considerations in order to predict the flow very well. So that creates an issue for us, and then we must use some novel methods different methods of trying to come upon a solution for the pressure field based on certain innovations which we have discussed the last time. Um, so this time we are talking about compressible flow solution. So the first and foremost point is that density is no longer invariant, as I said. So this opens up as well as closes some avenues for us, but we no longer need to, like since it's closer to reality, this kind of consideration, we are a little bit more free from the burdens of trying to look for a way to replicate things because this is more true to the physics. Um, Sound speed now in this condition when we are dealing with compressible flows, what does compressibility really mean? And incompressible and compressible, what we're talking about. Often one rule of thumb that comes up is that if Mach number is greater than 0.3, then we can say that it is compressible, which is true. But basically the main definition of compressibility is that density changes with pressure. Okay, density changes with pressure. So this density change with respect to pressure becomes more dominant after for like air or any gas when the Mach number is above 0.3, and then we look at the compressible region, right? So that's why this rule of thumb comes into play. So now I have a question for you. Like if I have like a candle flame kind of event kind at the flow around the candle. So will I consider my flow to be incompressible in that condition, or will I consider it to be to be compressible, given that my density is variable to temperature? I hope you are able to understand. Basically, I'm asking you that if I have something in which case the density changes with pressure are not considerable, but I have temperature changes um, and density changes because of the temperature, then what do I consider it? How do I treat the flow as incompressible or incompressible? So in that condition, actually you consider it to be incompressible itself because by using the various coupling available in the equations, we are able to sort of get the density variation due to temperature. But the main criteria for distinguishing between compressible and incompressible flow is that density is invariant with pressure in incompressible flow and it is variant in case of the compressible. So then in this condition, the sound speed becomes important. So sound speed is something that dictates how information travels. So when we are dealing with incompressible flows, generally the rate at which the information travels is way larger than the rate of the flow at which the flow is flowing. Therefore, the time scales are so different that we don't really consider speed of sound because that doesn't play an important role in our physics. But when we're dealing with compressible flows, since the speed of the flow is comparable to that of the speed of sound, therefore it can no longer be considered to be trivial. It's not trivial for us anymore. The sound speed starts to play an important role. And wave phenomena such as shock and expansion waves, fans become important when we are dealing with compressible flows. And these are intricately tied to the speed of sound. Okay. So then another concept that we had discussed earlier as well is about the concept of characteristics, which we also covered extensively during this week. So basically, what happens is that we try to plot an x versus t diagram, and our objective is to sort of plot straight lines such that each line is the slope of each line represents the speed of the flow. So basically, we had discussed this earlier also, and maybe diagram. We were looking at something like wave over here. This I had discussed when we were starting to discuss about the wave equation solutions when we shifted from the and how this wave gets transmitted as it is to some time to some other location. I haven't drawn it very well, but basically it's the same thing. So in this case also the example that I frequently use wherein I was speaking about like when I speak about a river and I say that someone dumps some ink into it and then the ink flows and this ink, this region which is full of ink just travels along the river and then it just becomes and it comes over. So basically that is an example of convection as we spoke before. And that is also something that is dependent on the characteristics because characteristics will essentially tell you how your solution will be carried from place A to place B because of convection. So wave equations generally are like what we have spoken about earlier also wave equations. So characteristics are an important are importantly associated with the wave equation. Right. And one more point that will come up in the lectures as well is that for discontinuities, the speed of the discontinuity is the average of the speed of the characteristic towards its left and towards its right. An important thing to note over here is that expansion waves are not discontinuities. So expansion fans basically what is their objective? Their objective is to equalize the pressure in case there is some pressure uh, disparity. But expansion fans basically are isentropic in nature. So they are not a discontinuity. A shock is a discontinuity because that is not isentropic. It doesn't gradually change the conditions from point A to point B. It is a sudden discontinuous change. So shocks are discontinuities, whereas expansion fans are isentropic processes. I hope this is something that you've already learned in the finance as well. And right. So another thing that in CFD is important for us and CFD and characteristics together is about the characteristics at the domain boundaries. So basically, whenever we are looking at a CFD domain, we have certain boundaries associated with it, which we've talked about before, where we apply the boundary conditions. So these boundaries also are affected in compressible flows. These are also affected by the speed of sound, and there are various ways in which we get information about how to treat the boundary because of the characteristic. And we'll see how it's like one of the questions in this today's talk. So basically, the crux of the matter is that at each boundary, there are three characteristics which are propagating at the speed of u, that is the speed of flow, u minus c, speed of speed of the flow minus the speed of the sound, and u plus c, which is speed of the flow plus the speed of and the number of characteristics that are passing across the said boundary, which is a boundary, which is our concern, that indicates what needs to be prescribed at that said boundary. Like how much information needs to be taken from outside and how much of the information is coming from within. Then another topic that was discussed in this week's total lecture was flux splitting for Euler equations. So basically, when we are trying to solve Euler equations, when we are looking at flux splitting, this is a purely sort of for our numerical ease that we do this activity. So, like there are two ways which were basically discussed in the lectures. One was flux splitting based on the characteristic values, and this is also equivalent to the flux splitting due to wave speed, like wave speed splitting and flux splitting due to based on characteristics are equivalent. So essentially, in that case, we just sort of separate out the parts of the flux vector which are associated with the right running waves or right running flux components and left running flux components. Please keep in mind when we are talking about all of this, we are looking at a 1D system. So when, for example, if you're going to look at a 3D system, it might not be as simple as how we are representing it over here. Basically, in that case also you will have to sort of look at the direction in which the flow is flowing in order to decide whether it's a positive or a negative, like this plus or a minus component of the flux. But in that case, there will be other ways to look at it. But right now, please make sure that you understand that we are discussing only about one dimension. Okay, so then this was the one that was associated with the flux splitting based on the characteristics, which is equivalent to the flux splitting based on the wave speed. These are both covered under the Steger-Warming, the Steger scheme. And the jar building scheme was also discussed, in which you sort of you just separate out the pressure terms from the density terms. Once again, because like as we know, when we move into more deeper into CFD and etc., that solving for pressure and density is tricky, and pressure is especially a troublesome term. And therefore, if you split the vector into two parts, one with the pressure and one without, we're able to give them separate treatments, which saves our which might help us to sort of circumvent divergence or any numerical problems. Okay, so this is just like a brief overview of whatever was discussed in class during this time. So now let's look into some questions. So the question, let's have a look at the question is, it says a subsonic flow that satisfies 1D Euler equations is moving along positive x direction at a domain boundary. Such a flow has. So now we are talking about the domain boundary. So it's a subsonic. So u is less than c. Okay. So let's make a diagram of the characteristics. Let's see the three characters, that is u plus c, u minus c, and u, how would you say? So then u is less than c. And where is it going? It's moving along the positive x direction. U is less than c, but it's still a positive value. So this is what the u characteristics is going to be. Then u plus c it says. Then the slope will increase. The sorry, verify u, and then I have u plus c, right? So the slope should be greater for u plus c, that is why I'm placing this. And then I have u minus c. So then since u is less than c, this will come more towards my other side of the negative characteristic, going towards the other side. This is a wave phenomenon that will travel away from the boundary towards the root, since this is the boundary. And then you have u minus c. So then basically at the boundary I have two right running moving waves and one left running waves. Okay, so let's just have a look at the question again. It told me that the u, basically the subsonic flow, is moving in the positive x direction. This is my x. At a domain boundary, such a flow has, yeah. So then one of the characteristics, which is, yeah, the initial, right, A. One of the characters moving outside the domain. Another characteristic is also moving outside the domain, and one is moving into the domain because u minus c is negative because of this piece of information. Right. Okay, so when we have this system, now that we have like seen how it looks like at the boundary, basically what it's trying to tell you is that like some information is going to be like, this information is coming from inside the domain, because over here this entire area is the domain. Okay, So this information is coming from inside the domain. Meanwhile, this information which is associated with u minus 3 must come from outside the domain, that is over here. Okay. So this outside the domain. So how does that happen? Basically, that means that you're at the boundary. You need to specify. You need to specify some physics at the bottom. For a subsonic outflow, typically what we, if you would see your answer fluent, etc., uh, then you will see that it asks you to give you the, it asks you to give the exit pressure. Okay, why is it asking you to give you exit pressure when you are dealing with a subsonic outflow is because of this characteristic. So this characteristic basically tells us that okay, I need some information from outside of my domain in order to complete my solution. Okay, that is makes some sense. Then let's have a look at this question. An Inviscid-Burgers equation allows only acoustic waves and shock waves as possible solutions. The diagram is given below where see u is equals to 0 is 1 if x mod is less than 1 by 3 and 0 if x mod is less than 1 is greater than 1 by 3. So over here in this diagram, if you will have a look at it with this movement, see what's happening. So basically, for the regions that are beyond this 1 by 3, 1 by 3, 1 by 3, we have straight characteristics. Okay, let's just give a similar. So our characteristics beyond x equals to like x. So in this region, our u is equal to 1, and anywhere outside this region, our u is equal to 0. Okay, so basically we're going to have like these straight characteristics all across the rest of the domain, and inside the domain, like in between these also, we are going to have a lot of characteristics which are going to be parallel to this and have a slope of 1. Okay, so one thing that was not noted in this diagram, like I saw when I was going through this, I did observe that the diagram is slightly long, because it's telling you that 1 by 3 is still here, meanwhile also telling you that u is equal to 0 over here. Starts from this point, so this is contradictory. Basically, this is wrong. Okay. Essentially, this is your 1 by 3. Okay, so from this point forward, basically what you're going to have is that this is your last characteristic that is that has a slope of 1, and here you will start having the slope of 0. Sorry, you will start going to have like a constant x equals to constant. So this is how it will be. So you see what the problem was, that basically what they said is that 1 by 3 is still some here this location, and that was misleading. Essentially, as soon as that region where u it starts to become straight, that region is where the it should end. Like basically this region where according to whatever our problem statement is, we need to understand that at x equals to 1 by 3, you are not going to have any more velocity associated with the characteristics. Anyway, so what is our question? The question. The question was basically, when will A meet S? Okay. So then A refers to this entire expansion fan. Okay. Expansion fan. So we are just going to look at our information that we got from beginning. So this is my shock that I have over here, and this shock originates from this point where that I have just shown you. So let's see how we can get the equation for the shock. So basically, it's asking us how, where, when these two lines are going to meet. Okay, since it's an expansion fan, therefore I'm not going to like so the edge of this expansion fan will meet the shock curve, so therefore I'm going to get this the equation of this line and the equation of this line. Okay, so we need to calculate the equation of these both lines. So it's going to go by a knowledge of the equation of this equation of edge of A. Okay. So in that case, we have over here x equals to mt plus c. Okay. This is how I'm going to write it. It's the reverse of what it is, right? But that's like reverse line equation. And so what do I have over here? So the x in this case is minus 1 by 3. I know the m I know from whatever the problem is, it's 1. Okay. I need the c, and and I know that at minus 1 by 3 comma 0, yeah, 1 minus 1 comma 3 is a part of this solution. Okay. So then lies on this. How do I know this? I know this from this. I need to come up with an expression for my x. So x is going to be 1 t was 0 in this case equals to c. Okay, so then I have minus 1 by 3 equals to c. So basically my x is going to be t. Okay, so t minus 1 by 3, here is my first line's equation. Then I need to find equation of s. Okay, for equation of s I'm going to take help of whatever I mentioned in the beginning of the class, um, that the slope of the discontinuity is basically the average of the slope at the either side of the discontinuity. Like these two are intersecting, right, and so are these two, and they have certain velocities associated with them, and you're going to average them both to know the velocity of the shock. So based on that, the m for the x equals to mt plus c. So when we have x equals to mt plus c, in this case, again we know the x. Okay, we know one point that lies on it is 1 comma 1 by 3 comma 0 lies on it, lies on this. This again we know from the diagram and from like basically just reducing down to the smallest characteristic is intersecting. So that lies on, so that point of intersection is basically like this shock is going to start from this point, or it's going to lie on that. Actually, the shock is not going to start from that point, or basically. Um, anyway, so 1 by 3 comma 0 lies on this, and I know my m is 1 plus 0 by 2, right? So basically what I'm going to have is that 1 by 3 is equals to c. So basically my equation of x for the shock, that is the equation that is associated with the shock, is going to be 0.5 t plus 1, right? Okay, so now you just equate these both and come up with the time t. So when x1 is equals to x2, then t minus 1 and 3 is equals to 5 plus 3. That's what equal to 4 by 3. So after 4 by 3 seconds, this shock is going to meet with the edge of the expansion plan. Okay, so basically what you had to do is you just had to find out the equation of the lines associated with S and the lines associated with the expansion plan. So you need to have some understanding of what is happening in both of those cases. So basically, expansion fan's edge is going to match up with the characteristic lines, with the like the slope of the last characteristic line associated with the expansion fan is going to be the same as the slope of these rest of these characteristics. That is one. And for the shock, we had learned earlier that basically you're just going to average out the slopes of the right running as well as the left, the characteristic lying on the right and the characteristic line on the left, and when you average it you get the slope for the short or the distance. So that's how you found out the equations of both of these lines, and by studying the graph you'll be able to fairly simply be able to understand which point lies where. So one important thing in this question was that this diagram was wrong. Okay, basically they had given some uh, like some wrong information about the location of the characteristics. So that you need to figure out in case there is some error, then it was asked. Let's move on to the next question. Okay, so now we are talking about flux vector splitting. So here we have when the flux vector split Euler equation is integrated using first order upwind scheme. Okay, for spatial derivative, the discretization will be as follows. So it's telling me that the flux vector split is integrated using first order upwind. So when we are talking about upwind scheme, that means that we have split the flux in terms of the right turning characteristics and the left turning characteristics, or also the you can also say the wave speed splitting. So when I'm going to have a first order upwind scheme on either side. Basically, what I want to do, what my objective is that whether the flux is in left direction or in the right direction, I should be able to apply an equivalent of forward space. Okay, like sorry, backward space. Equivalent of backward space. So basically, what I mean by that is that based on the direction, like if I have my I over here and I have I plus one over here, I minus one over here. And what's happening is that my flow is moving this. The flow is moving in this direction, then what that means is that I have to take information from here. If arrow was the other way around, this is the basic definition of momentum that we already discussed earlier. So in this case, I minus 1 is the one that is getting information from the vector. I'm trying to find a solution at I. Upwinding means that I'm going to take it from the previous cell through which the flow flew through. So the flow passed through this I minus 1 before I, so I'm going to take information from there. And in this case, when the flow velocity is the opposite, then the flow has gone through the cell I plus 1 before I, so I have to take information from I plus 1. This would be a case of F3 ds, sorry, Fs, and this would be F3 ds. Okay, so here I'm using the backward space. So then the answer to my question is that how do I solve this, right? So it's asking me that you have to represent expression that ui n plus 1. How are you going to write it? Okay, for this kind of positive. So here already the answers become pretty clear that when we are dealing with positive characteristics, we are dealing with FTDS. So it says that this is one. And when we are dealing with the negative characteristics, we are going to be dealing with FTX. Okay. So just a second, please. The point that I was making was that based on the direction of the flow, you will be able to decide what sort of scheme you should use for upload. So in this case, the correct answer is B. There's another correct answer, so please find it and let me know what that correct answer is. Okay. The second correct answer associated with this question is D, because basically whatever I have put in words and whatever the B is telling you um, in this condition is also what the D option is showing. Okay, so this is a fairly theoretical question. Wave speed splitting is used as this expression in which scheme? So we talked about two schemes in the beginning. One was associated with the pressure splitting, so that was the jar building pressure splitting, and the wave splitting was which ones? Can anyone write in the chat box that which of the options is right for the wave speed splitting? Okay, so the wave speed splitting is also equivalent to the flux splitting based on characteristics. This is the Sager warming scheme. It's something that was clearly given in your class notes as well. So basically, these are just names. It would be good if you can remember them. But the crux of the matter is basically is that the stagger warming scheme is related to this the flux scalar splitting as well as the wave speed splitting. So that is based upon something upon the information travel. Meanwhile, for the jar building scheme, what is happening is that we are just separating the pressure terms from the rest of the flux. Okay, so these are just two approaches. The names and all are not very important at this stage. Maybe later on, if you're developing a code or something and you want to read up on the various methods, that time this might be important. So it's good to know these things. The next question is the initial condition of wave is provided in the diagram below. With the passage of time, it would emerge into this wave. I'm given a UX diagram. It's asking me whether what is it? Is it a a centered expansion fan, a non-centered expansion fan, weak shock wave running towards left and strong shock wave running towards right, weak shock wave running towards right and strong shock running towards left. So how do I figure this out? Here, what I try to do is that I'm going to try to draw the characteristics. This is. And now this is a UT diagram of course. So I need an XT diagram in order to make sense out of this. This correspondingly drag in XT. Here I have E over here and X 16. So at x equals to 0, right? So basically, before this point, all of my this is a negative part. Let's do this case the velocity is something negative. So velocity is negative in this entire part. Velocity is negative. What does that mean? That in my xt diagram, these are going to be somewhat like this. Let's say so these characteristics are going to be pointing somewhere like this. Okay, this is the information that I have, and then what's happening is that till now it was constant, then slowly it stops to become that constant around this point around this point. These characteristics, they start to switch their shape out. Sorry, then these characteristics, they about this point, they are kind of like they change their direction to orient more along. This one. So basically, we need to just convert whatever exercise is given, like diagram is given over here, the the UT diagram to an XT diagram. Okay, so we know that for like if U is negative, then my characteristics are going to be left running. Okay, so till what point are my characteristics left running? Till this point where it is mentioned over here is equal to 0. Right. So till this point I'm dealing with negative characteristics. Okay, but these negative characteristics are also changing their shape. Essentially, they were negative till here, but they had the same slope for until this point. Until this point, they have the same slope. They are not veering away from that. But then there is some difference in the slope from this point, and so basically, they're just going to sort of behave in this fashion. Okay, and then they get to a point where now they are starting to slightly become positive. Okay, they become positive, more positive, just keep on getting more and more positive until say this point. Getting basically the slope keeps on becoming more and more. So and then basically finally what's going to happen is that these characteristics, since you're able to see a point where the u is constant, these are once again going to become parallel to each other. Okay, so what does this look like? So there's a physical confusion of this things. Clean it up a bit. So we have some interesting information from around this point to this point. Okay, and this is an expansion. Okay, why is it an expansion fan? Because first of all, it's not a shock, as you can see. Because if it was a shock, then I would be having some intersecting characteristics. So if I have intersecting characteristics where they go and clash into each other, such as like this, then I would know that there's a presence of a shock. But that's not what's happening. These characteristics are sort of diverging, they're moving away from each other. So that refers to an expansion fan, and that expansion fan is being represented from around here to here. In case it's unclear, this is the region of the expansion fan. Okay, so yeah, that should be it. Essentially, what you need to do is that you just need to take some time and draw the characteristics which are associated with the different velocities shown over here. So there are two three kinds of information you can get from the graph. One is if the direction of the velocity is negative, then what's going to happen is that the characteristics are going to be left running. Meanwhile, the characteristics will be right running when the velocity is greater than 0. Okay, and the slope keeps on changing based on the value of u that you are. And another question we have on here is on flux splitting. So flux splitting F plus max 0 to U is this okay. Okay, so what kind of flux splitting is being used in this example? Is it Jabilgin? Is it Steger warming? Is it Van Gogh? Pressure terms are separated. So I need an answer in the chat box now. I've given you the information required to come up with the answer. Hello? Hello? Yes, sir. Thank you. Thank you. Who collected? Sorry? The answer over here is the Javelin scheme, which is based on the splitting pressure. Hello? Okay, okay. Thank you. Right. So we have the Javelin scheme as answer of this question. The pressure splitting in Javelin scheme is done as follows for -1 n to +1 n. So this is something you can also find in your lectures. The answer to this is A. We look at this question. This might be right. So in a shock tube before diaphragm rupture, the thermodynamic states in region L and R are as follows. Um, L state. Right. So basically, on the L side we have 1 kg per meter cube is the density. The U is 0. The U is 0 on both sides. Oh, oh, is it? Just a minute. I'm sorry, I just this. Now is it okay? The voice? I think it should be okay now. I have connected my earphones again. Right. So basically, it's giving us some thermodynamic properties which will help us to predict in which direction the flow should move. Okay. And over here, the pressure is 10 times that on the right hand side. The pressure is 10 times that on the right hand side. So as soon as this diaphragm will burst, basically what will happen is that the flow will move in the right direction. Okay. So after the diaphragm rupture, normal shock run towards L. We'll look at all that. Um
contact discontinuity, that is this, that interface run towards the right. Yeah, this is at least a right answer. Okay, so basically since the pressure is higher on the right, on the left hand side, so when the diaphragm is going to just get ruptured, so all the high pressure flow is going to try to move towards the low pressure region, and therefore that discontinuity between the fluids at the left hand section versus the fluids on the right hand section, that interface is known as a content as a contact discontinuity, and that will go from left to right. Okay, and right. So what is going to happen is that this continuity, the interface between the fluid at the left and the right, is going to run from left to right. Why? Because the pressure at the left hand side is higher. So the high pressure fluids are going to move towards the low pressure region. Okay, so the contact discontinuity runs towards the right. That is a correct answer. Then it's asking us whether there is a normal shock and where normal shock and expansion wave and how they will run. So what happens is that when we have a high pressure region and a low pressure region, so these contact the normal shock as well as the expansion wave, what they're trying to do is to sort of equalize the pressure throughout the um, domain. So the normal shock, what will happen is that the normal shock will run towards R, I think that should be the right answer, and the expansion wave towards L. Yeah, yeah, that's my take on it.